Welcome to Grandpa's Late Nights. Come in, kiddo, pull the blanket up over your shoulders the way you like it, and let the pillow take the weight of your head. There's no hurry here. There's never any hurry here. The porch light's on, the kettle's long gone cold, and the whole house has gone that soft kind of quiet that only happens well after everyone sensible has gone to bed. Which, I suppose, means it's just you and me and the low hum of the night. Before we get going, I want to ask you something, and you don't have to answer out loud. Where in the world are you listening from tonight? Some of you are tucked in somewhere it's raining. Some of you have a window cracked open to a warm summer dark. Some of you are on a train, or a long drive, or lying flat on your back staring at a ceiling you know every crack of by now. Wherever you are, whatever hour it is in your corner of the night, I'm glad you're here. It's a good thing, having a little company at this end of the day. And if you find these slow, rambling nights help you drift off, a quiet like and a subscribe genuinely help this sleepy little channel keep the porch light burning. Small fellas like me really do lean on it. To those of you who've already subscribed, well, thank you kindly. You keep an old man company more than you know. Now, I'll make you the same promise I always make. I'm going to talk slowly, and I'm going to talk gently. And you are under no obligation whatsoever to follow every word. If you drift off before I'm done, that's not a failure, kiddo, that's the whole point. The ideas will still be here in the morning, patient as ever. You don't have to hold on to anything tonight. You don't have to understand every last piece of it. You just have to let it wash over you. Like the sound of rain on a roof you're safe under, I'll do the carrying. You just rest. I'll tell you what I want to talk about tonight, and it's a funny one. It's about time. Not time like where did the years go, though we could talk about that too some evening. No, I mean time the way you measure it. The tick of it. The second, the minute, the hour. How people like you and me, over thousands and thousands of years, slowly, clumsily, stubbornly, figured out how to catch hold of something as slippery as a passing moment and pin a number on it. And here's the strange thing I want to leave you with, the thing that surprised even me when I first turned it over. For almost all of human history, when a person said time, what they really meant, underneath it all, was the turning of the earth beneath the sun. A shadow crossing the ground, that was time. The world rolling over, the light moving, the dark coming on. Time was just the planet doing its slow turn, and we watched the turning and called it the day. But then something happened. Slowly, over centuries, we built machines that kept time better than the earth itself did. And eventually, and this is the part that gets me, eventually we decided the earth wasn't good enough anymore. We looked at the planet under our feet, the great spinning ball that had defined a day for every creature that ever lived, and we said, no, you're not steady enough. You wobble. You're slowing down. You can't be trusted to tell us what a second is. So we fired the sun. That's the honest way to put it. We took the job of keeping time away from the sky and the spinning world, and we handed it to something almost impossibly small, to a single kind of atom, humming away in a laboratory. Here's the exact moment it happened, and I want you to just let this number roll over you. You don't need to memorize it. In the year 1967, a gathering of the world's careful, patient measurement people, the sort of folks who fret over the 12th decimal place, got together and agreed on a new meaning for the word second. And the new meaning was this. 1 second is the time it takes for a certain kind of atom, an atom of cesium, to vibrate 9,192,000,000. 631,770 times, 9 billion and some change every single second. That's the heartbeat we chose. 91926317770. That specific peculiar number is now, quietly, what a second means. Not the sun. Not the turning of the world. The trembling of an atom too small to ever see. And I know how strange that sounds when you're lying there in the warm dark. Why on earth would anybody do that? Why take something as natural as a sunrise and swap it out for the shivering of an atom in a box? That's the whole story I want to tell you tonight, slow and easy, all the way from the very beginning. From a stick in the ground casting a shadow to that humming cesium atom. And by the end you'll see it wasn't madness at all. It was, in its own quiet way, one of the most useful things people ever did. It's part of why the little map on your phone knows where you are. But we've got a long, gentle road to walk before we get there, and there's no rush at all. So let's go back. Way, way back. Back before clocks, before gears, before glass. Back to the oldest way of telling time there ever was, which is simply this. You put something up so it casts a shadow, and you watch the shadow move. That's it. That's the beginning of everything we're going to talk about. A vertical thing, a stick, a stone, a pillar, standing up in the sunlight. The old word for it is a lovely one. A gnomon. Say it slow, it almost sounds like something out of a bedtime story. A gnomon. All it is an upright object that throws a shadow, and the clever part, the thing our distant ancestors noticed, is that the shadow doesn't just sit there. As the sun crawls across the sky through the day, the shadow swings around the base of the stick, and it changes length too. Long and stretched out in the early morning when the sun's low, short and stubby at midday when the sun's high overhead, long again in the evening, reaching out the other way as the sun sinks. So the shadow carries two pieces of information at once, if you learn to read it. Which direction it points tells you roughly what time of day it is, and how long it is tells you something about the season, because the noon sun rides higher in summer and lower in winter. All of that hidden in the shadow of a plain stick. People worked this out an unimaginably long time ago, and honestly, when you think about a person kneeling in the dust, watching a line of shade creep across the ground, and understanding what it meant, it's a rather tender thing. The first clock was just paying attention. Now the Egyptians, who are going to keep turning up in our story tonight, they took this simple idea and made it into a proper instrument. Around 3,500 years ago, we're talking somewhere near 1,500 years before the Common Era, in the age of a pharaoh called Thutmose III. They were using what we now call shadow clocks, and these were rather charming little devices. Picture a flat bar laid along the ground with an upright piece at one end, so the whole thing makes an L shape. The upright end casts a shadow back along the flat bar, and the bar is marked off into sections. As the shadow falls across those marks, it tells you which part of the day you're in. And here's the small, homely detail I love about it. In the morning, you'd set the instrument up with the tall end pointing east toward the rising sun, so the shadow fell westward across the marks. Then, at midday, when the sun crossed over to the other half of the sky, you had to physically turn the whole thing around. You'd pick it up and swing it so the tall end now faced west, and the afternoon shadow would fall the other way. Turn it east in the morning, west in the afternoon. There's something so human about that, isn't there? Getting up, walking over and turning your clock around at lunchtime because the sun's gone and changed sides on you. It makes you feel close to those people across all those thousands of years. They were just trying to know when the day was getting on, same as we do. The Egyptians didn't stop at little L-shaped bars either, they thought big. You've seen pictures of the obelisks, those tall, tapering stone needles that reach up toward the sky. Well, an obelisk is really just an enormous gnomon, a monumental stick. Stand one of those up in an open square, and its long shadow sweeps across the ground through the day like the hand of a clock the size of a courtyard. Morning, and the shadow's thrown far to one side. Noon, and it's at its shortest, pointing true. Evening, and it stretches away in the other direction. And because the noon shadow is longest in the depths of winter and shortest at the height of summer, the obelisk quietly marked out the turning of the whole year as well. The longest day, the shortest day, all written on the pavement in shade. The Romans, who loved to borrow a good idea and make it grander, actually took an Egyptian obelisk and built a giant sundial around it. There was one in Rome, a great open expanse of paving with the markings laid into it, and the obelisk's shadow moving over it all. We know about it partly because a Roman writer named Pliny wrote it down, described this enormous public timepiece, this solarium, in the heart of the city. Imagine strolling through ancient Rome and glancing at the ground to read the hour off the shadow of a stolen Egyptian monument. People have always found ways to make the time feel important and grand and a little bit showy. Now here's where I have to tell you about something a bit peculiar, and I want you to just let it drift past you, because it's the kind of thing that's lovely to think about right as you're falling asleep. The hours those ancient people used were not the hours you and I use. Not really. You see, they did something that seems perfectly sensible at first. They took the daylight from sunrise to sunset, and they split it into 12 parts. 12 hours of daylight, and then they took the night, sunset to sunrise, and split that into 12 as well. 12 hours of dark, neat and tidy, 12 and 12. But think about it for a moment, slowly. In the summer, the days are long and the nights are short. In the winter, it's the other way round, long nights and short days. So if you always chop the daylight into exactly 12 pieces, then in summer each daylight hour has to be stretched out longer to fill all that extra light, and in winter each daylight hour has to be squeezed down short to fit into the little bit of daylight there is. Their hours breathed with the seasons. A summer daylight hour was genuinely longer than a winter daylight hour. The very length of an hour changed depending on the time of year. We call those temporal hours or seasonal hours, and to us it sounds almost impossible to live with. Imagine an hour that isn't always the same size. Imagine the hour getting longer in June and shorter in December, and everybody just going along with it, because the whole point of the hour was to divide up the daylight, and there was simply more daylight to divide in summer. It worked perfectly well for a world that lived by the sun. If your hours are just names for portions of daylight, then of course they stretch and shrink with the daylight. Nobody was bothered. Nobody was trying to catch a train. That way of keeping time, those breathing seasonal hours, they lasted an astonishingly long while, all the way through the ancient world and deep into Europe, right up until the day machines came along that couldn't do it, that couldn't make an hour stretch and shrink, and forced everyone onto hours that were all the same size. But we'll get to those machines. We've got a good long way yet, and there's no need to hurry toward them. Let me stay with the sun a little longer, because I want to plant a small seed in your mind, gently, one that's going to matter enormously by the end of our story. And it's this: The sun, for all its glory, for all that it ruled timekeeping for thousands of years, is actually a rather poor clock. A bad clock even, and the ancient sundial makers slowly bumped up against this fact, and it must have puzzled them terribly. Here's the trouble. You'd think the sun crosses the sky at a nice, steady, even pace, the same every day. But it doesn't. The sun runs a little fast at some times of the year and a little slow at others. Sometimes it reaches its highest point, its true noon, a bit early, sometimes a bit late. This happens for reasons buried in the shape of the Earth's path around the sun and the tilt of the world, and you don't need to hold any of that in your head tonight. The thing to feel is just this: if you set a really accurate mechanical clock beside a really accurate sundial and let them run for a year, they would disagree. Not by a little. They'd wander apart and back together, drifting as much as 16 minutes off from each other, one way and then the other, over the course of the year. 16 minutes. That's a real gap. That's the difference between catching something and missing it. And it means the shadow on the sundial and the hands on a good clock simply do not tell the same story. There's even a name for the correction you'd have to apply to turn sundial time into proper, steady clock time. It's called the equation of time. And if you've ever seen a fancy old sundial with a strange figure-8 loop drawn on it, a sort of lopsided infinity sign, that loop is the sun's wandering, drawn out. It's called an analemma, and it's really a little map of how the sun runs fast and slow through the year, so you know how much to add or subtract to get the honest time. So keep that quietly in the back of your mind as you drift. Even at the very start of our story, before any gears or springs or atoms, there was already a faint crack in the foundation. The sun, the great original clock, the thing everyone trusted absolutely, was itself a little bit unreliable, a little bit wonky. 16 minutes worth of wonky. Nobody could have guessed, back then, how far that small crack would eventually run. But it's there. Hold on to it, loosely, the way you'd hold a hand in the dark. Now the daytime, the sunlit hours, those the Egyptians and their neighbours had a decent handle on. Shadows, gnomons, obelisks, sundials. But there's a problem that must have nagged at people for as long as there have been people. And it's this. What do you do at night? When the sun's gone down and there are no shadows at all? How do you tell the time in the dark? Well, for that, the ancients looked up. The Egyptians in particular watched the stars, and they noticed that as the night wore on, particular groups of stars would rise up over the horizon one after another in a steady procession. They picked out a set of these star groups, 36 of them in all, marching through the sky across the year. And we call them the Deccan stars, and on any given night you'd see a sequence of these star groups climb into view, one following the last, and by counting them off you could divide the night into portions. It worked out through the way they tracked across the seasons to about 12 divisions of the night. 12 star hours of darkness to match, more or less, the 12 shadow hours of the day. And there, quietly, in that ancient Egyptian habit of splitting the daylight into 12 and the night into 12, is where our 24-hour day was born. 12 and 12, day and night. It came down to us across all those centuries, and we never let go of it. When you glance at a clock tonight and see the hours run 1 to 12, and then round again, you are looking at a very, very old Egyptian idea about the sun and the Deccan stars still ticking away on your wall. But the hours, they only got us so far. What about the smaller pieces, the minutes, the seconds, the finer chopping up of time? For that, we owe a different people, a bit further east, in the land between the rivers, the Babylonians. Now, the Babylonians had a way of counting that seems strange to us, but which turns out to be rather brilliant. Where you and I count in tens, everything built on 10 and 100 and 1,000, they counted in 60s. Base 60, we call it. 60 was their magic number. And that's why, to this very day, there are 60 seconds in a minute and 60 minutes in an hour. Not because 60 is natural or obvious, but because thousands of years ago, a people in ancient Mesopotamia liked to reckon in 60s, and their mathematics was so useful that it stuck, and it stuck, and it never came unstuck. 60 little seconds make a minute. 60 of those minutes make an hour. 24 of those hours make a day, 12 from the Egyptian sun and 12 from the Egyptian night. Multiply it all out and you get 86,400 seconds in a single day. 86,400. That number is going to come back to visit us later in the night, so let it settle somewhere soft in your memory. For now, just marvel, gently, that every time you say half past or quarter to, you are speaking a language part Egyptian and part Babylonian, thousands of years old, and you never even had to learn it. It was just handed to you, worn smooth by all the hands it passed through. So, we have the day sorted, after a fashion. Shadows for the light, stars for the dark, hours from Egypt, minutes and seconds from Babylon. But there's still that stubborn problem sitting there, and it's a bigger one than the night. Because stars only help you on a clear night, and shadows only help you in the sun. What about a cloudy day? What about indoors, in a windowless room? What about when you simply cannot see the sky at all? The sun and the stars, for all their faithfulness, had a monopoly on time. If you couldn't see them, you were lost. And people don't much like being at the mercy of the weather. So somewhere along the way, a wonderful idea arrived. What if you could measure time with something that didn't depend on the sky at all? What if you could measure it with water? And this, kiddo, is where our story takes its first real turn, away from the heavens and down to the ground, to something you could hold in your hands and carry into a dark room. The water clock. The ancients gave it a rather dramatic name. They called it the clepsydra, which means, and I do love this, the water thief. As if the water were quietly stealing away the hours, drop by drop. The idea at its simplest is beautiful. You take a vessel, a bowl or a jar, and you make a small hole in the bottom. You fill it with water, and the water begins to drip or trickle out through the hole. And as the water level slowly sinks down inside the vessel, it passes a series of marks scored on the inner wall. Each mark is an hour, or a portion of an hour. You don't need the sun. You don't need the stars. You don't need to see anything but the falling water level and the marks it uncovers. Time, at last, indoors and after dark and under cloud. Time you could carry with you. The oldest one of these that has actually survived down to us is Egyptian again. Those Egyptians really were busy with time. It comes from around 1400 years before the Common Era, in the age of a pharaoh named Amenhotep III, and it was found in the great temple complex at Karnak. It's a stone vessel, shaped a little like a flower pot, with a small hole near the base for the water to escape, and rows of marks on the inside to read the hours off as the water drained away. Just imagine a temple priest 3,500 years ago, in the deep of the night, needing to know when to perform some sacred rite, And instead of squinting at the stars through the dark, simply glancing at the level of water sinking in a stone pot. There's a kind of quiet magic in that. The night no longer had him at its mercy. He'd stolen a little of its power. The water thief did its work. But, and there's always a but, that's how these stories go, and it's a comforting sort of rhythm, isn't it? The way one clever idea always turns up a new little problem. The water clock had a flaw baked right into it. A problem of physics that the ancients would have felt long before they could explain it. And it's this. When your vessel is full, right to the brim, the water is heavy. All that water pressing down means it pushes out through the little hole quickly, in a good strong trickle. But as the water drains away and the level drops, there's less and less water left, and so there's less weight pressing down, less pressure behind it. And with less pressure, the water dribbles out more and more slowly. The flow doesn't stay steady. It starts fast and finishes slow. Do you see the trouble that makes? If the water rushes out at the start and only creeps out at the end, then your hour marks can't be evenly spaced. The first hour would drain a great gush of water, and the last hour would drain only a thin dribble. A naive water clock, just a pot with a hole, runs unevenly. It races at the beginning of its measure and dawdles at the end. And for something whose whole job is to divide time into fair, equal pieces, that's a genuine headache. So the old engineers, patient and clever, went to work on it, and this is really the first time in our story that a person had to sit down and outwit the physical world to keep good time. It would not be the last. They found a couple of ways around the problem. One trick was to shape the vessel cunningly, to slope its walls, to make it wider at the top and narrower toward the bottom, so that as the pressure dropped, the changing shape of the water's surface compensated, and the marks could be spaced to match. Get the taper of the walls just right, and the falling level would touch each hour mark at the proper moment, even as the flow itself sped and slowed. A shape carved to cancel out a flaw in the flow. The other trick was cleverer still, and it's the beginning of an idea that runs all the way through the history of clocks. Instead of letting the vessel drain from full to empty with all that changing pressure, why not keep the water level constant? Rig it so a steady supply keeps the reservoir always topped up to the very same height, with any excess spilling away over an overflow so the pressure never drops at all. If the level never falls, the pressure never falls, and if the pressure never falls, the water flows out at one unchanging, faithful rate from the first hour to the last. Hold the source steady, and the measure comes out even. And that idea, steady the thing that drives the clock, and the clock will keep true. That's not just a trick for water pots. That is, in a way, the secret heart of this entire long story we're telling tonight. Every great leap forward in timekeeping, right up to that humming cesium atom I promised you, is really some new and cleverer answer to the very same question those ancient engineers were kneeling over. How do you find something in this restless world that beats at a perfectly steady rate? Something that doesn't rush and dawdle. Something you can trust to divide up time into pieces that are all exactly, faithfully, the same size. The Egyptians found their first answer in the shape of a pot and the level of some water. It's a humble beginning. A stone vessel with a hole in it, dripping in the dark of a temple. But it's a real one, and everything else grows out of it. Because once you've had the thought, once you've realized that time doesn't have to come from the sky, that you can build a machine of a sort that ticks off the hours on its own, right there on the table in front of you, rain or shine, day or night, well, there's no going back from a thought like that. The genie's out. From here on, people are going to keep asking that same question over and over for the next 3,000 years. What can we find that beats perfectly, steadily, forever? And their answers are going to get stranger and more wonderful than any Egyptian priest could ever have dreamed. From falling water, they'll move to swinging pendulums. From swinging pendulums to trembling crystals of quartz. And from trembling quartz, at the very last, to the shivering of a single kind of atom, 9 billion times a second, in a sealed and silent chamber. But every one of those, every single leap, is just another way of asking the water clock's question. What beats truly? What can we trust? So rest easy now, kiddo. We've come a long way already. Just you and me, in the quiet, from a shadow crawling across the dust in the Egyptian sun, to an obelisk's shade sweeping a Roman square, to the hours that breathed with the seasons, to the water thief dripping faithfully in the temple dark. And we've barely begun. There's the whole clever business of gears and escapements still ahead of us, and a swinging lamp in a cathedral, and a lonely carpenter who'll spend 40 years of his life chasing a problem that killed sailors by the thousand. But all of that can wait. None of it is going anywhere. The story will still be here, patient as a shadow, whenever you want to come back to it. For now, just let the water drip, slow and even and unhurried, down through the marks on the old stone pot. Let it carry the hours away for you, gently, one soft drop at a time, so you don't have to carry them yourself. There's nothing you need to keep hold of tonight. Not a single thing. Now, here's a man worth knowing about. His name was Cesium, and he lived in Alexandria, that great, humming city at the mouth of the Nile, sometime in the 3rd century before the Common Era. We don't know the precise year of his birth or his death. We don't have a portrait. What we have is Vitruvius, the Roman writer, who described his work centuries later with the kind of admiration you reserve for someone who genuinely changed how things worked. Cesium was a barber's son, or so the story goes, and whether or not that part is exactly right, there's something I find quietly wonderful about it. The idea that the most important improvement to timekeeping in 1,000 years came not from a royal court or a temple priesthood, but from someone who grew up watching ordinary life, ordinary people, ordinary water. Because his insight was beautifully simple. And like most beautifully simple insights, it required a very careful look at something everyone else had stopped noticing. The problem with the clepsydra, the water clock, the one we talked about as you were drifting off, was pressure, you remember. As the vessel empties, the water level falls, and with less water pressing down from above, the flow through the little hole at the bottom slows, so the marks on the inside wall couldn't be evenly spaced. The hours shrank and stretched in ways that were hard to predict and harder still to correct. It was a clock that told you roughly when it was, which is rather like a compass that points roughly north. Useful, but only to a point. Cesium solved it with a device so elegant you almost want to laugh, because it looks obvious once you see it. Instead of letting the vessel drain directly, he arranged for a separate reservoir, a container above the main bowl that always stayed nearly full. Fresh water flowed in from above just as fast as it flowed out through the hole below. And here's the part that matters. Because the water level in that reservoir was held constant, the pressure on the outflow hole was constant. The flow was constant. The ticking of the water, if you'll allow me to call it that, was constant. For the first time, a water clock dripped at the same rate at the 5th hour of the night as it had at the first. And then he added something else. Inside the main receiving bowl, he placed a float, a small disc that rose as the water level climbed. Attached to the float was a pointer, and attached to the pointer was a dial or a column marked with hours. As the water rose, steady and predictable, the float rose with it, and the pointer climbed past the markings, hour by hour, almost like a tiny hand sweeping slowly upward through the dark. It was, in a sense, the first clock with a readable display, not a passive vessel you had to peer inside, but a mechanism that showed you the time, automatically, without anyone needing to check. Vitruvius called it remarkable, and it was. Cesium had invented, somewhere around the 3rd century before the Common Era, what engineers would much later call a feedback control system, a way of making a process regulate itself. He didn't have that language, of course. He just had the problem and the patience to look at it long enough to see the solution hiding inside it. Now, the Greeks were practical about their water clocks, in ways that tell you a great deal about what they valued. In the courts of ancient Athens, the clepsydra was used to time speeches. Each speaker received a fixed allotment of water, and when the water ran out, their time was up. There is something almost gentle about that image. No bell, no gavel, just a stone vessel quietly emptying, and the slow verdict of flowing water saying, "Your time is done. Let someone else speak now." Not unfair, not unkind, just water. There's a story too. You may want to file this one gently under probably true, but charmingly embellished, that Plato, the philosopher, designed a water clock that could serve as an alarm. The idea was that water would fill a chamber until it reached a pipe. The pressure would then force air through the pipe, and the pipe would whistle. A water-powered whistle. A clock that woke you. Whether Plato really built one, or whether his students simply credited him with the idea because he was the sort of man you'd associate with a clever device, we can't be entirely sure. But the image stays with you, doesn't it? The father of Western philosophy lying in his bed in Athens, waiting for his water to blow its little trumpet and call him to the day. Sleep past it if you like, kiddo, he'd understand. But here is where I want to pause and turn the lamp slightly sideways. Because the story of clocks, the real story, is not a story that belongs only to the Greeks and the Romans and eventually the Europeans. And if you've ever read a history of timekeeping that jumps straight from the ancient Mediterranean to medieval church towers without stopping anywhere in between, well, it left something out, something quite large. Turn your attention, if you will, to China, to the Song dynasty, which flourished from the 10th to the 13th centuries, a period of extraordinary intellectual energy. In the city of Kaifeng, which was at the time one of the largest and most sophisticated cities in the world, an official named Song was given a commission. He was an astronomer, a diplomat, a polymath of the kind that any era would be proud of, and what he was asked to build was an astronomical clock tower. Song completed it in the year 1094. The tower stood roughly 10 meters tall, about the height of a 3-story building. Inside it was a water-powered wheel, enormous and complex, turning step by step and driving a cascade of gears and levers and small figures that emerged at the correct moments to display the time, the position of the moon, the movements of the stars. It was a spectacular piece of engineering by any standard. But what matters most for our story, what gives Song's tower its particular place in the history of time, is one component at its heart. The mechanism that controlled the wheel's motion, that made it turn not in a rush, but in measured, countable steps. Scholars who have studied the surviving records and reconstructed the device call it an escapement. It released the wheel one increment at a time, in a controlled, regular beat. And it was doing this in 1094, in China, before any equivalent mechanism appeared in Europe. I say this not to diminish what European clockmakers eventually built. I say it because the real history is richer and wider than the version that gets told most often, and you deserve the richer version, even here, in the half-dark of wherever you are tonight. A little over a century after Susong, on the other side of the world, in what is now southeastern Turkey, in a city called Diyarbakir, under the patronage of the Artukid dynasty, a scholar and engineer named Al-Jazari was putting the finishing touches on a book. He completed it in 1206. The Book of Knowledge of Ingenious Mechanical Devices. And among the devices it described and illustrated in careful, surviving manuscripts were water clocks and candle clocks of breathtaking complexity, clocks with moving automata, little mechanical figures that marked the hours by raising a hand or striking a cymbal, moons and birds and doors that opened and closed on the turning of a wheel. Al-Jazari's clocks were not only functional, they were theatrical. They were designed to delight, to show that measuring time was not only a practical necessity, but a thing that could be made beautiful. So take a moment, as you rest, to let that sink in. In 1206, while Europe was still a few decades away from its first mechanical church tower clocks, the Islamic world was building water-powered automata that could put on a performance at the stroke of the hour. These things coexisted. The history of time does not run in a single straight line from one civilization to the next. It bloomed in many places at once, like lights coming on in different windows across a very large, very dark city. Now, there is one more water-based timekeeper I should mention before we leave this particular chapter. It is humbler than Susong's tower, quieter than Al-Jazari's automata, but in its way it was more enduringly practical than any of them. The hourglass. By the 14th century, the hourglass, or sandglass, because what flows through it is very fine, very dry sand, not water, had become a fixture on European ships. And the reason for this is straightforward once you think about it. A ship moves, a ship pitches and rolls and lurches. Water in a clepsydra sloshes, the surface tilts. The outflow changes. The clock becomes unreliable at exactly the moment you need it most, which is when you're at sea and trying desperately to know what time it is. Sand doesn't slosh, not in the same way. A fine, dry stream of sand flowing through a narrow neck between two glass bulbs is not much disturbed by the motion of a ship. You could hold an hourglass at an angle and it would still run, not perfectly, but close enough to be useful when the alternative was no clock at all. Sailors turned their hourglasses religiously, typically every half hour or every hour, keeping a tally on a logboard. The ship's boy, whose job it was to watch the glass and turn it before it ran out, was, in a real sense, the ship's timekeeper. If he fell asleep, the log was wrong. If the log was wrong, the navigator's reckoning was wrong. And if the navigator's reckoning was wrong, then the ship was somewhere other than where anyone thought it was. That is a problem we will come back to, because it becomes, in time, one of the most consequential problems in the history of exploration. But not yet. Not quite yet. First, we need to leave the world of flowing water and flowing sand and enter a different world entirely. The world of the tick. Something changed in Europe in the late 13th century. Somewhere, And historians still argue about exactly where, exactly when, because the evidence is fragmentary and spread across monastery accounts and civic records and architectural surveys. Somewhere in the years around 1275 to 1300, someone built a clock that did not rely on water or shadow or sand. It relied on a falling weight and a very clever little device that turned that weight's fall into something controlled, something measured, something you could count. The device was called a verge and foliot escapement. Let me describe it as gently as I can, because understanding it, even roughly, is worth something. Imagine a vertical rod, the verge, with two small pallets attached to it, one above the other, sticking out at angles. Above this rod hangs a horizontal bar called the foliot with small weights at each end. Below the rod, a toothed wheel, the crown wheel, is driven by the falling weight. As the wheel turns, its teeth engage one pallet, which pushes the foliot to rotate in one direction. But as it rotates, the other pallet swings into the path of the wheel, stops it, and then gets pushed back, rotating the foliot the other way, back and forth, back and forth. Each swing of the foliot is one counted increment of the wheel's turning. Each swing is one tick. It is the escapement, this device or its descendants, that makes a mechanical clock a clock. Without it, the weight falls all at once, the wheel spins freely, nothing is measured. With it, the weight falls one tiny step at a time, each step released by the swinging of the foliot, and each step is a heartbeat of the machine. The escapement is what gives a clock its tick, and it is what transforms stored energy, a heavy weight, later a coiled spring, into counted, regular, trustworthy time. These early clocks were large, heavy, built into towers of churches and cathedrals and town halls across Europe, from England to Italy to France. And here is something I find rather charming about them. Many of them had no dial at all. No hands, no face, nothing to look at. They had a bell. That was the point. Ring the canonical hours, the set times of prayer that organized monastic life, so that monks and nuns, scattered across a garden or a cloister or a field, knew when to stop what they were doing and go to chapel. The word clock itself, as it came into English from the Old French and Latin, and ultimately a Celtic root, means bell. Clocker. A clock was a bell ringer. A mechanical bell ringer that didn't need a person pulling the rope. They weren't accurate, these first clocks, not by any standard we would recognize. They lost or gained somewhere between 15 minutes and half an hour every single day. You had to adjust them against a sundial which still held that authority, and even then, you were only approximately right. But here's the thing, it almost didn't matter for their primary purpose. If the bell rang and it was close enough to the canonical hour, the monks went to chapel. If the bell rang and it was technically a few minutes early or late, well, God, presumably, made allowances. But something was happening beneath the surface. Something that would quietly rearrange the whole of European life over the following centuries. Because a mechanical clock, even an inaccurate one, does not breathe. It does not stretch and shrink with the seasons the way a sundial's hours do, expanding in summer and contracting in winter. Its foliot swings at a rate set by its weight and its length, and it swings that same rate in January as in July. It makes equal hours, not seasonal hours, not temporal hours, equal hours, every one the same length, summer and winter alike. This sounds like a small thing. It was not a small thing. It slowly, steadily restructured the way people thought about time. Work became measurable not by how much sun was left in the sky, but by how many hours you'd been at it. Agreements could be made, meet at the third hour, The contract runs for 2 hours, with a precision that seasonal sundial time could never quite deliver. Time became a grid, a universal grid, imposed not by nature but by a machine. And over the following century, that grid would spread across Europe, ringing from towers in 100 cities, ticking away in 1,000 churches, quietly organizing the world. Now, a handful of clockmakers in the 14th century began to ask a different question than how do we make a clock ring the hours more reliably? They asked something grander. They asked, what if the clock could show you not just the time, but the whole turning of the heavens? Richard of Wallingford was the abbot of St. Albans Abbey in England, and around 1330 he designed and began work on an astronomical clock for his abbey. It would show the tides, the moon's phases, the positions of the sun and moon in the zodiac. A cosmos in miniature ticking above the nave. Richard died before it was finished. He was ill for most of his abbacy, with a disease that disfigured his face. Leprosy, some sources suggest, though we can't be certain, and the clock was completed by others after him. But the conception was his, and it was extraordinary for its time, a machine that didn't just count hours, but modelled the sky. Even more elaborate, and completed somewhat later, was the astrarium of Giovanni de Dondi, an Italian physician and scholar from Padua. De Dondi spent 16 years on it. 16 years. He completed it in 1364, and what he built was a 7-faced machine with dials for the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn, each face showing the planet's position according to the Ptolemaic model of the cosmos, which was how the universe was understood at the time. Every gear ratio was calculated to match the known cycles of each planet's orbit. It was, in the most literal sense, a model of the universe that you could hold, or rather stand in front of, and watch turning. The astrarium itself doesn't survive, but de Dondi left detailed written instructions for rebuilding it, and working replicas have been constructed from those instructions. They are remarkable to look at. And what they tell you about these early European clockmakers is something important. They did not think of themselves merely as making a practical tool for ringing bells or organizing schedules. They thought of themselves as building a model of creation. Time, to them, was not just a convenience. It was the mechanism of the cosmos itself, and to master time was to understand, perhaps even to touch, the mind of God. There's something very human in that, and very beautiful, whatever you happen to believe. But let's keep moving, because the clock is about to become something it had never been before. It's about to get small. Through all of this, through Wallingford's Abbey clock and de Dondi's planetary marvel, the driving force was a falling weight. Hang a heavy stone or a bag of lead from a cord, wind the cord around an axle, and gravity does the rest, slowly pulling the weight toward the floor and turning the gears as it goes. Simple, reliable, powerful, but utterly impractical if you want to carry a clock with you. You can't put a hanging weight in your pocket. You can't take it on a horse, or up a staircase, or certainly not to sea. In the 15th century, someone, and the historical record on this is genuinely muddy, so I'll spare you a confident claim I can't fully support, figured out how to replace the falling weight with a coiled spring. Wind it tight, and it pushes. Let it unwind slowly through the escapement, and you have a clock small enough to sit on a table. Small enough, eventually, to wear around your neck or carry in your hand. The early portable timepieces became fashionable in the early 1500s. The ones attributed to a German craftsman named Peter Henlein from Nuremberg. are sometimes called Nuremberg eggs because of their rounded, oval shape, though whether Henlein was truly the first or simply the most famous is one of those historical questions that tends to generate more heat than light. What matters is that by the early 16th century, there were small spring-driven clocks being made in Germany that a person of means could carry and own personally. Time had become, for the first time in history, a private possession. Not just a public bell ringing over the town square, but a small ticking thing in your own hand. Spring drive introduced a problem, though. A coiled spring pushes hardest when it's fully wound and most weakly when it's almost unwound, which means the clock would run fast when freshly wound and slow as the spring tired, like a sprinter who starts with a burst and trails off toward the end of the race. The clockmakers knew this, and one of them, the exact attribution is, again, contested, solved it with a device called a fusee. Picture a cone-shaped pulley, shaped rather like a twisted tower, connected by a cord to the spring barrel. When the spring is fully wound and at its strongest, the cord pulls from the narrow top of the cone, giving the spring less leverage. As the spring unwinds and weakens, the cord pulls from the wider bottom, giving it more. The varying geometry exactly, or nearly exactly, compensates for the varying force. The clock runs evenly. The fusee is one of those solutions that, once you understand the problem, feels almost inevitable. The elegance of it is real, and it was invented sometime in the 15th century by someone whose name we don't know for certain, and it kept mechanical watches and portable clocks ticking at roughly uniform rates for the better part of 300 years. But roughly uniform wasn't going to be enough. Not in the end. Not for what was coming. We need to talk about a swinging lamp. Now, I want to be careful here, because the story as it's usually told has been polished smooth by centuries of retelling, and the polishing may have changed it in places. The traditional account goes like this. In the year 1582, a young Galileo Galilei, he's about 18 years old, a medical student, not yet the physicist who will rewrite our understanding of motion and the heavens, is sitting in the Cathedral of Pisa. This was a place he knew well. And during a service, his attention wanders from the liturgy to a bronze lamp hanging from the ceiling, swaying gently on its chain after someone had lit it or moved it. Galileo watches it swing. He times it against his own pulse, because there are no watches in this cathedral, or none that he has access to. And he notices something. The lamp's swing, whether large or small, seems to take the same amount of time. A wide arc and a narrow arc complete in the same number of heartbeats. This story comes to us largely through Galileo's biographer, Vincenzo Viviani, who wrote it down decades after the fact, after Galileo's death. Whether it happened exactly as described, in precisely 1582, in exactly that cathedral with that lamp, we can't say for certain. Viviani was devoted to Galileo's memory and not above dramatic embellishment in service of a good story. What we can say is that the underlying physics is real. Galileo did investigate the behavior of pendulums. He did discover, through genuine and careful experiment, what we now call isochronism, the property of a pendulum by which its period, its time per swing, is very nearly independent of how far it swings. A wide arc and a narrow arc take, to a useful approximation, the same amount of time. This is counterintuitive. You'd think a wider swing would take longer, because the pendulum has farther to travel. And it does have farther to travel. But it's also moving faster, because gravity pulls it harder at the bottom of a wider arc. And those two effects, farther distance, faster speed, nearly cancel each other out. The period stays nearly constant. That nearly will come back to haunt the clockmakers in a moment. But for now, the discovery was astonishing. A swinging weight was a potential timekeeper. A natural, physical, consistent timekeeper. Not dependent on the craftsman's skill, but on the laws of the universe itself. Galileo spent years investigating pendulums. Near the end of his life, blind and under house arrest, he designed a pendulum clock. He dictated the design to his son, who sketched it out. But he died in 1642 with the clock unbuilt. It was left to someone else. And that someone else arrived very quickly. Christian Huygens was a Dutch mathematician and scientist, brilliant, meticulous, and very much in the right place at the right time, which was the Netherlands in the 1650s, one of the intellectual centres of the world. In 1656, using Galileo's insight about isochronism, Huygens designed and built the first working pendulum clock. He patented it in 1657. And in a single stroke, he did something that centuries of escapement refinement had not managed to do. He made clocks accurate. I want to say that plainly, because the numbers are so striking they deserve to sit in the air for a moment. Before Huygens' pendulum clock, the best mechanical clocks of the day lost or gained on the order of 15 minutes a day. Maybe more. After Huygens' pendulum clock, the error was around 15 seconds a day. Not 15 minutes, 15 seconds. An improvement of roughly 60 times, achieved with a single new component. A swinging weight, hung from the movement, governing the beat of the escapement. What made the pendulum so superior to the foliot was a deep physical principle. The foliot's rate depended on how you adjusted it. Slide the little weights in or out along the bar, and the clock ran faster or slower. But the adjustment was arbitrary, a matter of craft and feel. The pendulum's rate depended on its length, and the length of a pendulum, once set, is a fact about the physical world, governed by gravity, the same everywhere on the surface of the earth. You couldn't easily drift a pendulum clock the way you could a foliot clock, because you'd have to physically change the rod's length. It had a natural, self-asserting beat. It argued back. Huygens understood the mathematics of it deeply. He knew, for instance, that a simple circular arc was only approximately isochronous, that a pendulum swinging in a wide arc would swing slightly more slowly than one swinging narrowly. A tiny but real discrepancy called circular error. He worked out that the truly isochronous path, the curve along which a pendulum would always take exactly the same time, regardless of arc width, was not a circle, but a different curve altogether, called a cycloid. And he designed what he called cycloidal cheeks, curved metal plates that the pendulum string pressed against during its swing, guiding the bob along a cycloidal rather than circular path, and so correcting the error mathematically, built into the machine itself. This is the kind of detail that makes clockmaking, when you look at it closely, feel almost like philosophy made physical. Huygens wasn't just trying to build something that ticked regularly. He was trying to build something whose regularity was guaranteed by geometry, by mathematical truth, not by approximation or skill. He wanted a clock that was right because the universe said so. And it worked. Not perfectly, no clock is perfect, but the pendulum clock of 1656 was, by the standards of everything that had come before it, astonishingly good. Within a year or two of its appearance, clockmakers across Europe were building pendulum clocks. The old foliot clocks were being quietly retired or converted. A new era of precision had begun. There is one more thing I want to tell you about pendulums tonight. just one, because it connects to something that will matter later in our story. A pendulum that takes exactly 1 second per swing, what clockmakers came to call the seconds pendulum, needs to be a very specific length, about 0.994 meters. Very nearly 1 meter, just a hair's breadth shy of a meter. So close that it seems almost intentional. And it didn't escape the notice of the natural philosophers of the late 17th century, who were beginning to think about units of measurement and whether there was a natural, universal length, something not tied to the length of a king's foot or the width of a barleycorn, but to the physical world itself. If 1 meter were simply defined as the length of the seconds pendulum, then the unit of length and the unit of time would be woven together by gravity and mathematics into a single coherent system. It was a beautiful idea. Elegant, almost too elegant. And it very nearly happened. The story of why it didn't, and what was used instead, belongs to a slightly different chapter of history. But tonight, as you drift, I want you to carry that small, gleaming fact with you, that the length of time and the length of space once almost became the same thing. Tied together by a swinging weight in the quiet mathematics of a pendulum's arc. Things are connected in ways we don't always expect. The universe seems to enjoy that sort of coincidence. And here we are. Here you are, perhaps growing heavier in the dark, your breathing slower, the ceiling a little further away than it was when we started. Here we are at the close of one long, patient leap and the beginning of the next. The pendulum gave us accuracy. But accuracy, as it turns out, was not enough. Because the pendulum, for all its mathematical elegance, is sensitive to things you might not think to worry about. Temperature, the rod that carries the swinging bob, if it's made of metal, and it usually was, gets slightly longer when it's warm and slightly shorter when it's cold. And a longer pendulum swings more slowly, not by much, but by enough. Enough to matter. And there are bigger troubles ahead still. Bigger than temperature, bigger than the pendulum. Because even as clockmakers in the 1650s and 1660s were learning to build accurate clocks, another problem was gathering offshore, quite literally, on the decks of sailing ships, crossing oceans, without any reliable way of knowing where they were. Thousands of miles of open water and no landmark and no clock that could survive the heaving of the sea. That problem is where we're going next. But not tonight. Not just yet. Let those pendulums swing for a while in the dark. Let the beat of the escapement slow and steady itself, the way your own breathing is slowing now, and your heartbeat, settling into whatever rhythm it finds when you stop asking anything of it. So, temperature. Let's stay with it a moment, because this is where the clockmakers earned their reputation for the kind of stubbornness that borders on philosophy. The problem is simple to describe and maddening to fix. Metal expands when it's warm and contracts when it's cold. A pendulum rod made of iron or steel is no exception. Warm day, longer rod, slower swing. Cold night, shorter rod, faster swing. And a grandfather clock standing in a room that swings from a warm afternoon to a cool morning can lose or gain several seconds over the course of a day simply because the air around it changed temperature. Not because anything broke. Not because anything wore out. Just because the world has seasons and rooms have drafts and pendulums are made of matter. It bothered people enormously. And that's one of the things I love about this particular chapter of the story, the people it bothered and the ingenuity they brought to bear on a problem that might seem, from the outside, too small to deserve such care. George Graham was a London clockmaker born in 1673, a member of the Clockmakers' Company and a Fellow of the Royal Society by the end of his career, which tells you something about how seriously the world of natural philosophy and the world of skilled craft had begun to overlap. In 1721, that's 64 years after Huygens' first pendulum clock, Graham looked at the temperature problem and proposed a solution that is almost too elegant. He filled the bob of the pendulum, the weight at the bottom that does the swinging, not with lead or iron, but with mercury. A sealed cylinder of liquid mercury. And here is the trick. When the air warms and the pendulum rod grows longer, pushing the bob downward and slowing the swing, the mercury inside the bob also warms and expands, but mercury expands upward, raising the effective center of mass of the bob. The two effects almost exactly cancel. The rod gets longer, the mercury rises, and the pendulum's rate stays very nearly the same. A clock that didn't know what season it was. It wasn't perfect, but it was remarkably good. And it represents a kind of thinking that would run through clockmaking for the next 2 centuries, not fighting the laws of nature, but designing a system that turns 2 errors into each other's correction. Harrison had his own version. John Harrison, and we'll come back to him because he is the great protagonist of this whole chapter, the man whose shadow falls over everything. Harrison in the 1720s, early in his career, still a young carpenter clockmaker in Lincolnshire, came up with what's called the gridiron pendulum. 9 rods, alternating between 2 metals, steel and brass. Steel and brass expand at different rates when heated. So by threading them together in a specific arrangement, 5 rods of steel, 4 of brass, their expansions working against each other, Harrison created a pendulum that expanded and contracted in ways that cancelled themselves out. The bob stayed at the same effective height, the period stayed the same, and the clock kept better time regardless of the weather. He made it from first principles, having worked out the coefficients of expansion himself. This was a man who understood physics, not from books, though he read them when he could, but from handling materials, from measuring, from the kind of deep, practical knowledge that is sometimes mistaken for simple craft. It was not simple. It was science with sawdust on its hands. But even all of this, the gridiron pendulum, Graham's mercury bob, the anchor escapement that allowed a small arc and a smooth, unhurried swing, even all of this was still not enough for a certain category of problem. Because a pendulum clock, however accurate, cannot go to sea. You can close your eyes and picture why if you like. A pendulum works because gravity pulls it back to center. It swings because it's given a tiny push and then released into the pure mathematics of a swinging arc and a restoring force. But on a ship, the floor is alive. It pitches, it rolls. The whole frame of the clock tilts and rights itself and tilts again in rhythms set by the ocean, rhythms that have nothing to do with the pendulum's own period. You can't separate one motion from the other. The sea swallows the pendulum's regularity without even trying. So for the critical, urgent, murderous problem of navigation at sea, the pendulum clock was useless, and navigation was urgent. Not abstractly. Lethally, let me explain the problem in the plainest terms I can, because it's one of those cases where the underlying geometry is very simple and the consequences were very large. Standing on a ship in the middle of the ocean, you can work out how far north or south you are, your latitude, without too much difficulty. You look at the pole star. You measure the angle of the sun at noon. These change predictably as you move north or south, and with the right tables you can pin down your latitude to within a few miles. Sailors had been doing this for centuries. But east or west, longitude, is a completely different creature. There is no star pinned over the equator the way Polaris sits over the North Pole. There is no natural landmark in the sky that tells you how far east or west you are. Because the Earth is rotating. East and west are not fixed directions in the heavens, they're expressions of time. The Earth spins 360 degrees in 24 hours. That works out to 15 degrees of longitude per hour. Or, to put it the other way round, for every 4 minutes of time, the Earth turns 1 degree. So if you know what time it is at a fixed reference point, say Greenwich, in England, and you know what time it is where you are right now, locally by the sun, the difference between those two times tells you exactly how far east or west you are. 4 minutes of difference, 1 degree of longitude. 60 minutes, 15 degrees. Simple. The problem is the word know. To know what time it is at Greenwich, when you're somewhere in the middle of the Atlantic Ocean, you need a clock. A clock you set before you left Greenwich. A clock that has been running correctly through weeks of pitching seas and salt air and temperature swings and the general violence of ocean travel. Every second that clock has lost or gained since leaving port adds error. A clock that loses just 3 seconds a day sounds like a very good clock. Over the 6 weeks of an Atlantic crossing, that's 3 minutes of accumulated error. 3 minutes of time difference is 3/4 of a degree of longitude. At the latitude of the Azores, that's about 50 miles. 50 miles in the wrong direction, on a featureless sea, with no GPS, no radio, no way of knowing which side of a reef you're on. 50 miles can be the difference between safe harbour and a shipwreck. And shipwrecks happened. The most terrible example from this period is the one that helped change history. In October of 1707, a fleet of Royal Navy ships under Admiral Sir Cloudesley Shovel was returning from Gibraltar, approaching the southwest coast of England in fog. The navigation was uncertain. The fleet believed itself to be clear of the Scilly Isles, a scatter of rocky islands off the tip of Cornwall, but they weren't. 4 ships struck the rocks. 4 ships in a single night. Roughly 1,400 to 2,000 sailors died. Sir Cloudesley Shovel himself was among them. The numbers are hard to hold. 1,400 to 2,000 people. And the disaster was not, in the most important sense, caused by bad weather or incompetent officers. It was caused by not knowing where they were. It was caused by the absence of a clock that could keep time at sea. 7 years later, in 1714, the British Parliament passed the Longitude Act. It offered a prize, the Longitude Prize, of up to £20,000 to anyone who could demonstrate a practical method for finding longitude to within half a degree on a voyage from Britain to the West Indies. £20,000 was an enormous sum. In today's terms, something in the tens of millions. The Board of Longitude was established to judge entries and award the prize. And the whole scientific and mechanical world turned its attention to the question. There were 2 serious competing approaches. One was astronomical. The moon moves against the background stars at a rate slow enough to track, but fast enough that its exact position at any moment is specific to that moment. If you could measure the moon's angle from a known star precisely enough, you could look it up in a table, a lunar distance table calculated in advance for the reference meridian, and deduce what time it was back at Greenwich. No clock required, just a sextant, a set of tables, and a head for arithmetic. This method was real. It worked. The Nautical Almanac, first published in 1767, provided exactly these lunar distance tables, and they were used by navigators for decades. The mathematician and astronomer Neville Maskelyne, who would become one of Harrison's great adversaries, championed this approach. But it had a fatal practical disadvantage. The calculations were long and difficult, requiring a trained navigator and hours of work, and the observations themselves demanded a level of steadiness and clarity that the motion of a ship made genuinely difficult. The other approach was mechanical. Build a clock. Make it survive the sea. And this is where John Harrison enters the story properly. Harrison was born in 1693 in Folby, Yorkshire, the son of a carpenter. He grew up in Lincolnshire and taught himself clockmaking as a young man, not from an apprenticeship in the London trade, but from books and observation and an almost ferocious natural aptitude. By his 20s, he was making clocks of unusual quality. By his 30s, he had already designed the gridiron pendulum and built a series of precision long-case clocks that demonstrated a level of mechanical understanding that the established London trade could barely explain. But longitude was the problem he had fixed on. And in 1730, he travelled to London to present his ideas to Edmund Halley. Yes, that Halley, the comet's namesake, who was then Astronomer Royal. Halley sent him to the great clockmaker George Graham. Graham received him warmly, lent him money without interest, and encouraged him to build his design. Harrison built it, and in 1735 he presented the Board of Longitude with H1. H1 is a remarkable object. It's large, you could put both your arms around it and nearly meet your hands on the other side. It runs not on a pendulum, but on two counter-swinging balances, connected by springs in such a way that the motion of the ship sets both swinging, and the two motions cancel each other out. It has no pendulum, because a pendulum is useless on a ship. Instead, it replaces the pendulum's restoring force with springs and the pendulum's isochronism with a very clever mechanical equivalence. The board was impressed enough to fund a sea trial. H1 sailed to Lisbon and back. It performed reasonably well, but not well enough. Harrison himself was his own harshest critic. He knew it could be improved. He went home and built H2, then H3. H2 he rejected fairly quickly. H3 occupied him for 17 years. He worked on it from 1737 to 1757, though he was simultaneously developing ideas about the balance wheel and spring regulation that he thought he could use more effectively in a different form entirely. And then he built H4. H4 is nothing like what you would expect after 3 massive sea clocks. It is a watch, about 13 centimeters across, the size of a large pocket watch, something you could hold comfortably in your palm. It looks, to modern eyes, almost normal, though the workmanship is extraordinary. Harrison completed it in 1759, when he was 66 years old. He had been working on the longitude problem for nearly 3 decades. The sea trial of H4 began in 1761. Harrison's son William sailed with it to Jamaica. The voyage lasted about 81 days each way. At the end of it, H4 had lost around 5 seconds. 5 seconds over 81 days, a rate of error so small it not only met the longitude prize requirements, it shattered them. 5 seconds. The act required performance equivalent to no more than 3 seconds per day to win the top prize. H4 averaged less than 1/10 of a second per day. It was, by the standards of the time, a clock from another century. The Board of Longitude did not simply hand Harrison the prize. This is where the story turns from triumph to something more complicated and, if you're still listening in the dark, perhaps more human. The board was sceptical, some of its members, particularly Maskelyne, who favoured the lunar distance method, were deeply reluctant to concede. They demanded another trial. There were questions about whether the result was a fluke. Harrison, who was nearly 70, complied. H4 sailed again. It performed brilliantly again. The board argued about technicalities. They asked for the design to be disclosed, the clock dismantled, copied, and verified. Harrison complied again. And still they hesitated. He spent years in this position, having demonstrably solved the problem and still not having received the prize. He petitioned Parliament directly. Eventually, in 1773, it was King George III himself who intervened. Harrison presented the case personally, and the king, in the wonderful phrase attributed to him, declared that he had been treated with cruel injustice. Parliament paid Harrison a sum of over £8,000, though he never received the formal longitude prize in the manner the Act had specified. He died 3 years later, in 1776, at the age of 82. A life's work, a career's worth of obstinacy and precision in the service of a single, specific, maddening problem. And the world changed because of it. The proof of just how completely the world changed came not long after Harrison's death. The navigator Larkham Kendall had been commissioned to build a copy of H4. It was called K1. This was part of the board's verification process, meant to prove the design could be replicated. And K1, this faithful copy, went to sea with Captain James Cook on his second voyage of discovery, beginning in 1772. Cook spent nearly 3 years at sea, circumnavigating the globe, mapping the Southern Ocean, charting coastlines that no European had ever traced. Through all of it, K1 was at his side. Cook's journals are not given to excessive sentiment. He was a practical man, more interested in latitude and soundings than in lyrical observation. But when he wrote about K1, he called it his trusty friend and his never-failing guide. A watch, copied from a Yorkshire carpenter's design, guiding a captain through waters nobody had ever charted. There is something quietly enormous about that image, if you let yourself sit with it. The chronometer, as the sea clock came to be called, had won. Lunar distances didn't vanish immediately. They coexisted with chronometers for decades, because not every ship could afford one and because trained navigators could still use the lunar method when needed. But the direction of the future was clear. The problem that had killed thousands of sailors, that had shaped the geopolitics of exploration and empire, that had occupied some of the sharpest minds of the 18th century, that problem had been solved by a carpenter from Yorkshire who taught himself horology from books and spent 30 years building the right clock. What remained was making it affordable. Harrison's H4 was a masterwork, but it was a one-of-a-kind object built by one man over decades of obsessive refinement. You couldn't simply send a Harrison watch on every ship in the Royal Navy. The work of turning the chronometer from a singular marvel into a reliable, replicable instrument fell to the generation that came after him. 2 names stand out. John Arnold and Thomas Earnshaw, working through the last decades of the 18th century and into the early 19th, developed a crucial mechanical innovation, the spring detent escapement. A detent is a small catching device, a kind of latch or lever, and the spring detent escapement replaced the older, more friction-prone designs with something lighter, more reliable and more consistent. It needed less oil, it disturbed the balance wheel less with each tick, and it could be made by skilled craftsmen who weren't Harrison. Between Arnold's refinements and Earnshaw's improvements, and there was between them the usual territory dispute over who invented exactly what, chronometers became manufacturable. By the early 19th century, the price of a marine chronometer had dropped by a factor of 10 or more from the levels of the 1760s. They appeared on ships of the Royal Navy as standard equipment. Merchant vessels carried them. The problem that Parliament had thought insoluble and had offered £20,000 to fix had, within a couple of generations, been transformed into a piece of standard marine hardware. Somewhere out in the dark beyond your window, if you could hear through the centuries, you might hear the ticking of those ships' chronometers, kept in their gimbaled boxes in the chart room, winding every day at a precise hour, the navigator noting any accumulated rate of gain or loss in the chronometer log. Ships that knew where they were. Seas that had become, if not tame, at least a little more comprehensible. And so the pendulum clock and the marine chronometer had, between them, given the world something it had never quite had before. Portable, reliable, accurate time. The kind of time you could carry with you. The kind of time that stayed the same when you moved. But a new question was forming at the edges of all this precision. Not an urgent question, not yet, but a philosophical one, and then slowly, as the instruments got better, a practical one too. How good could a clock get before it started running into the limits of the world itself? The pendulum had beaten the sun. The chronometer had beaten the sea. What happened when the clock got good enough to start asking questions about the Earth? Let me tell you about a clock called the Shortt synchrotome. William Shortt was a railway engineer. Not, at first glance, the kind of person you'd expect to build the world's most accurate pendulum clock. But he became fascinated with the precision limit problem, and in the early 1920s, 1921 to be specific, he collaborated with Frank Hope Jones and the Synchrotome Company of London to produce something that had never quite existed before. A clock in which the pendulum that did the keeping of time was separated from everything that might interfere with it. The system had two pendulums, a master and a slave. The master pendulum, the one that actually defined the beat, swung in a sealed, nearly evacuated tank. A near vacuum, no air resistance to slow it, no drafts to disturb it, no mechanical load from driving hands or ringing bells. It simply swung, in the dark, in the close to silence of its evacuated chamber, as free as a pendulum can physically be. Once a minute, a tiny electrical impulse from the slave clock gave it a small, precisely metered push to compensate for the trace of friction that even a near vacuum couldn't eliminate entirely. Other than that, the master pendulum was left alone to do what pendulums do. The slave pendulum drove the hands. The slave clock told people the time. The master clock simply was the time. The Shortt synchrotome was accurate to about a second per year. 1 second per year. Compare that to Huygens' pendulum clock in 1656, accurate to roughly 15 seconds per day. That's one step in human clockmaking, 300 years of refinement, and the improvement is more than 5,000 times. But the most interesting thing about the Shortt clock was not how accurate it was. The most interesting thing was what it revealed. When the clock was cross-checked against other Shortt clocks and against astronomical observations, something unexpected showed up. The clocks agreed with each other. But they didn't always agree with the Earth. The Earth's rotation, the phenomenon that had defined the second since the Egyptians divided the day into 86,400 parts, was not perfectly steady. It wobbled. It speeded slightly and slowed slightly. There were seasonal variations, small but measurable. There were irregular fluctuations, unpredictable in timing and cause. And the Shortt synchronome clock was so accurate that it could see these fluctuations. It could detect the Earth's own irregularities. This was the second time in the history of clocks that a mechanical timekeeper had overtaken the planet. The first time was Shortt's contemporary, the quartz clock, but we'll get to that. And, not for the last time, the instrument had outrun the phenomenon it was built to measure. Think about what that means for a moment, in the gentlest possible way. We built a device to measure the rotation of the Earth. We got so good at the device that the device could now measure the Earth's imperfections. The student had passed the teacher. The meter had exceeded the thing it was measuring. And if that were true, if the Earth's rotation was a slightly erratic thing, a clock that wobbled with the seasons and slowed over the centuries under the moon's patient gravitational pull, then the second, as defined by the Earth's rotation, was not a fixed, reliable quantity. It was a moving target. It depended on which day you measured it, which century, how you averaged. This was not immediately disqualifying. For most of human history, close enough was all anyone needed, and the Earth's rotational wobbles are tiny, milliseconds per day, usually far less. But precision has a way of demanding more precision. Once you can measure something accurately enough to see the wobble stops being ignorable. The clocks had arrived at a threshold. The kind of threshold where the answer to what time is it exactly begins to depend on what you mean by exactly and who or what you're trusting to tell you. And that, quietly, is where we are as we arrive at the next chapter. But we are not there yet. There are still a few more pieces to set in place before the ground shifts entirely. The Shortt clock was precise enough to catch the Earth wobbling, yes, but what happened next, what brought the question to a head and forced the world to make a formal decision, required an even more extraordinary kind of timekeeper. One that didn't swing at all, one that didn't tick in any mechanical sense, one that lived inside matter itself. But not yet. Not tonight, not this moment. For now, let those twin pendulums go on swinging, the master in its close, quiet vacuum, the slave dutifully turning the hands, the two of them in conversation with each other across a thread of electricity, steady and unhurried. Let the image rest there in the dark with you. A clock so good it caught the planet wobbling, a planet we had been trusting for 4,000 years. There's something almost tender about it, if you think of it that way. We didn't fire the Earth abruptly. We didn't decide one morning, arbitrarily, that we were done with sunrises as timekeepers. We built better and better instruments, and slowly, gently, the instruments began to reveal that the thing we'd been measuring against wasn't quite as reliable as we'd assumed. The Earth was doing its best. It had been doing its best for 4.5 billion years. But it was also a very large rock in space, subject to tidal forces and atmospheric loading and the slightly melting of polar ice, and 100 other things that made it spin subtly, measurably, undeniably unsteady. And we had built clocks that could see this. Maybe take a breath here. There's no rush. The night is long, and we're not done with the story yet. What comes next, the step that finally resolved the question the Shortt clock raised, that formally separated the second from the spinning Earth and bound it to something that cannot wobble, cannot slow, cannot melt at the poles, that step is still just ahead of us, somewhere in the middle of the 20th century. In a laboratory at a place called the National Physical Laboratory, with an element called Cesium and a kind of vibration so fast and so regular that it makes every pendulum that ever swung look like a rough guess. But that's the next part of the journey, and it will keep. For now, settle a little further in. Let the image of those twin short pendulums be the last thing you hold. Two swinging weights in the dark, so still and precise that they were reading the hiccups in the planet's spin, measuring the tiny slippages in the Earth's rotation the way you might notice, in a very quiet room, the sound of a clock running just slightly wrong. The clocks had gotten very, very good. And the Earth had been found to be a little less perfect than we thought. And somewhere out there, in a direction we couldn't quite see yet, someone was already beginning to ask whether there might be a better kind of pendulum altogether. Not one that swings, not one made of metal or glass or mercury, but one made of light and matter and a quantum fact about a single kind of atom. 9,192,631,770 times a second, as it would turn out. But we'll get there gently. And so we come, at last, to the part of the story where clocks stopped being personal and became public, where they stopped being towers and became networks, where what time is it stopped being a local question with a local answer, the sun is there, therefore it's noon, and became something that had to be negotiated across the entire surface of the Earth all at once. You can think of railways as the first force that made this necessary. Before trains, every town in Britain kept its own solar noon. Bristol was about 10 minutes behind London. Edinburgh was about 12.5 minutes behind London. Liverpool was about 12. None of this mattered much when the fastest thing on the road was a horse, because a horse doesn't run fast enough to make 12 minutes feel like a scheduling crisis. You arrive, you look at the local clock, you adjust. Fine. But a train runs fast enough to make 12 minutes very important indeed. And a train runs on a schedule printed in advance. And if Bristol's clocks say one thing and London's clocks say another, and the printed timetable says something else, you get confusion at best and collisions at worst. The railways made time a public infrastructure problem rather than a private astronomical one. The Great Western Railway adopted a single standard time, London time, Greenwich time, across its entire network in 1840. Other lines followed. By the late 1840s, the telegraph was spreading across Britain, and the telegraph could carry a time signal down a wire almost instantaneously, so a clock in Bristol could be kept synchronized to a clock in Greenwich without anyone having to carry a watch on horseback. By 1847 and 1848, most of the major British railway companies had adopted Greenwich Mean Time as their standard. The country's clocks, which for thousands of years had each pointed honestly at the local sun, were now being pulled into alignment around a single meridian on the outskirts of London. They resisted for a while. Some stations ran 2-minute hands, one for local time, one for railway time. Bristol had a clock on the Corn Exchange that ran dual faces for years. But the logic of coordination was too strong. By 1880, Greenwich Mean Time was legally adopted across Great Britain. The local sun had lost. A single institutional clock had won. And then the same argument played out across the whole world. In 1884, 41 delegates representing 25 nations gathered in Washington, D.C. for what was called the International Meridian Conference. They had one central question to answer: which meridian, which line of longitude on the surface of the Earth would be accepted as the 0 point? The place from which all longitude and all time would be measured. The French wanted Paris, others had their own preferences. But Greenwich already handled the vast majority of the world's maritime traffic. About 72% of the world's shipping at the time used charts based on the Greenwich meridian. It was not so much chosen as recognized. The prime meridian was declared to be the one passing through the Astronomer Royal's telescope at the Royal Observatory in Greenwich. The world was divided into time zones, each 15 degrees of longitude wide, each 1 hour apart. A global grid of coordinated time was drawn across the planet, and for the first time, "What time is it?" had an answer that could in principle be the same answer everywhere, adjusted by a predictable whole number offset. It was a remarkable achievement, and it rested on a definition of the second that almost nobody thought to question. A second was 186,400 of a mean solar day. One day has 24 hours, each hour has 60 minutes, each minute has 60 seconds. 24 times 60 times 60 gives you 86,400. So a second was simply a particular slice of the Earth's rotation. Time zones were offsets from Greenwich, yes, but underneath all of that, the fundamental unit, the second itself, was defined by the spin of the planet. Everything was still anchored to the turning Earth, just more neatly organized, and here is where the story turns, just slightly, in a direction that nobody at the 1884 conference was quite prepared for. Because the Earth, it turns out, is not the reliable clock they assumed it was. The moon has been stealing our spin for a very long time. Every time the moon pulls on Earth's oceans and raises a tide, and every time that tide sloshes up against the ocean floor and the continents, it creates a tiny frictional drag on the Earth's rotation. The tidal bulge on the near side of the Earth is pulled forward by the moon, and the ocean floor beneath it drags slightly against the spin. The effect is almost vanishingly small on any given day, but it accumulates. Over geological time, it adds up. The day is getting longer, not by much, by something like 1.5 to 2 milliseconds every century, which sounds like nothing, and over a human lifetime it really is nothing, but over millions of years it adds up to hours. The moon is also drifting away. The same tidal friction that slows the Earth's spin transfers angular momentum to the moon, nudging it into a slightly higher orbit. The moon recedes from us by about 3.5 to 4 centimeters every year. Slowly, gently, imperceptibly, the moon is edging away. And we can read the record of all this in the fossil record. Certain ancient corals lay down daily growth bands, thin regular layers that mark each day's growth the way tree rings mark each year. When geologists look at corals from roughly 600 million years ago, they find more daily bands per year than you'd expect. The reason is that back then, a day was only about 21 or 22 hours long. The Earth was spinning faster. There were more days in a year, perhaps 400 or more, because each day was shorter. The moon was closer. The tidal braking had not yet done its slow work. 600 million years of friction have shaved away those extra hours and stretched the day to the 24-hour cycle we experience now. And it will keep lengthening. Far in the future, so far it's almost meaningless to say, the day will be considerably longer still. So even the most elegant, practical definition of the second, 186,400 of a day, is a definition built on a clock that is running down. By the early 20th century, the precision of timekeeping had advanced far enough to actually detect this. Quartz clocks, which we're coming to in just a moment, and even the Shortt pendulum system you're drifting away from now, these instruments were steady enough to show that the Earth's rotation was not constant. It wobbled seasonally, as ice and oceans and atmospheric pressure redistributed mass around the globe. It jumped irregularly, probably due to interactions between the liquid outer core and the mantle. And it was slowly, stubbornly, irreversibly lengthening. The Earth was, in the strictest technical sense, a bad clock. A clock that neither gained nor lost a fixed amount, but one whose rate was subtly, unpredictably variable. This put the world's timekeepers in an awkward position. The second was defined by the Earth. But the Earth was unreliable. What do you do? The first answer, worked out in the 1950s and formally adopted in 1960, was to tie the second not to the Earth's rotation but to its orbit. The Earth goes around the Sun more steadily than it spins. The tropical year, the time from one spring equinox to the next, is more constant than the length of a day. So a new definition was proposed. The second would be 131,556,925.9747 of the tropical year 1900. Not the current year, not a recent year, but the year 1900, a specific, fixed historical orbit that could be calculated with precision and used as a reference. This was called ephemeris time. The ephemeris is an astronomical table of planetary positions, and ephemeris time was read from those tables rather than from the turning Earth. It was a reasonable idea. But it had a practical problem that turned out to be fatal. You couldn't actually measure ephemeris time directly in real time. To determine it precisely, you had to compare astronomical observations against mathematical predictions and average them over years. A single observation gave you a rough estimate. A reliable measurement required something like 9 years of accumulated data. The second had been redefined as something untouchable, something buried so deep in the mathematics of celestial mechanics that you could only know what time it was after the fact. As a scientific definition, it was an improvement. As a practical tool for synchronizing the world's clocks, it was almost useless. It was a stopgap, and everyone who understood what was happening knew it, because there was another possibility already on the table, a different kind of pendulum altogether. But first, let me tell you about crystals. In the early 19th century, physicists discovered that certain crystals, quartz among them, had a peculiar property. If you squeezed a quartz crystal, it produced a small electric charge. Press it, and you got voltage. And the reverse was also true. Apply a voltage across the crystal, and it flexed, it deformed slightly, it changed shape. This property was called piezoelectricity, from the Greek for press, piezo, because the electricity came from pressure. Now, what makes this interesting for timekeeping is what happens when you put that crystal into a circuit. If you cut a piece of quartz to a precise shape and size and drive it with an alternating voltage, the crystal will vibrate at a very specific, very stable, resonant frequency. It is, in effect, a tuning fork made of glass, but one that vibrates millions of times per second and barely notices that the temperature is changing or that someone bumped the table. Its resonant frequency is determined by its geometry and the laws of physics, and it is extremely consistent. Warren Marrison and J.W. Horton, working at Bell Telephone Laboratories in New York, built the first quartz clock in 1927. It was not a small object. It filled a room, or very nearly, but it worked. And it was, by the standards of the day, astonishing, where the best pendulum clocks of the era were accurate to within a fraction of a second per day. The first quartz clocks were accurate to within a small fraction of a second per year, something like 100-fold improvement. Better than pendulums by such a margin that, within a few years of the quartz clock's arrival, it became possible to do something that the pendulum had only hinted at, to sit in a laboratory and directly measure the irregularities in the Earth's rotation in real time. Not by painstaking comparison with planetary tables, but by simply comparing the clock to the sky and watching the sky fail to keep up. The clocks had, again, outrun the planet. Now, the thing inside every quartz watch and every quartz clock you have ever owned, the thing doing the actual timekeeping, is a tiny sliver of quartz vibrating at a frequency of exactly 32,768 cycles per second. That seems like a strangely specific number, and it is, but the reason for it is wonderful in its simplicity. 32,768 is 2 to the power of 15, 2 times itself, 15 times over. Inside the watch, that vibrating crystal is connected to a chain of tiny electronic circuits, each one a flip-flop that counts 2 pulses and outputs 1, a divide by 2 stage. 15 of those stages in a row, each one halving the frequency. 32,768 divided by 2 is 16,384. Divide by 2 again, 8,192. Again, 4,096. And you keep going, step by step down the chain, until after 15 halvings you arrive at exactly 1 pulse per second. The second hand ticks. The reason for 32,768 specifically is that it is the lowest power of 2 that falls in a range where a quartz crystal can be cut small enough to fit in a watch, vibrate stably, and be driven economically. Any lower power of 2 and the crystal gets too large or too slow to be practical. Any higher and the crystal gets more expensive and harder to make consistently. 32,768 is the engineering sweet spot, and because it's a power of 2, the divider chain is trivially simple, no complicated arithmetic, just a cascade of identical flip-flop circuits. An elegant hidden symmetry running inside your wristwatch, ticking 15 halvings per second. Forever, quartz watches became commercially available at the very end of the 1960s. The Seiko Astron, the world's first quartz wristwatch sold to the public, went on sale in Japan on Christmas Day of 1969. It cost about the same as a small car at the time. But the price would fall rapidly, and as it did, something remarkable happened to the watchmaking world. The Swiss watch industry had built its identity over centuries around the precision mechanical movement, the tightly wound mainspring, the escapement, the balance wheel, the craftsmanship of tiny gears and levers assembled by hand. Switzerland made the finest watches on earth. And then a piece of crystal on a circuit board came along and made all of that precision essentially irrelevant for everyday accuracy. A cheap quartz movement kept better time than almost any mechanical watch ever made. By the late 1970s and early 1980s, Swiss watchmaking was in crisis, factories closing, craftspeople out of work, an industry that had defined its nation's identity for generations suddenly under existential pressure from cheap electronics. The quartz revolution, they called it in the watch industry, but it felt more like a flood. Some Swiss makers survived by pivoting to luxury and tradition, a mechanical watch as jewellery, as heirloom, as art object, but the world of everyday timekeeping had been transformed permanently, quietly, almost overnight. Quartz was extraordinary, but it was not, in the end, the bottom of the well. There were people during all of this who had been asking a different question. Not how can we make a better vibrating object, but what is the most stable, most reliable, most universal oscillator that physics permits? And the answer they were converging on had nothing to do with crystals or pendulums or balance wheels. It had to do with atoms. Every atom of a given element behaves identically, not approximately identically, not nearly the same within manufacturing tolerances, but exactly identically to a precision that no human craft can match. Because every atom is made by the same laws of quantum physics, and quantum physics does not have tolerances. A cesium-133 atom in a laboratory in London, and a cesium-133 atom in a laboratory in Tokyo, and a cesium-133 atom on the far side of the galaxy are, to the best that physics can determine, the same in every relevant way. They have the same energy levels. They absorb and emit radiation at the same frequency. They are, in this specific sense, universal standards. The idea of using atomic transitions as a basis for timekeeping had been developing through the 1930s and 1940s, with important theoretical foundations laid by Isidore Rabi and later extended by Norman Ramsay. Rabi had worked out how to use magnetic resonance to probe atomic energy transitions with great precision. Ramsay devised a method, the separated oscillatory fields method, which would eventually earn him the Nobel Prize, that made those measurements far more precise by essentially asking the atom the same question twice at different moments and listening to how it answered. These were the techniques that made an atomic clock conceivable. And then it was built. Louis Essen and Jack Parry at the National Physical Laboratory in Teddington, the NPL, Britain's National Measurement Institute, completed the first accurate cesium atomic clock in 1955. The clock worked by taking a beam of cesium-133 atoms, selecting atoms in a particular energy state, passing them through a microwave field at a carefully controlled frequency, and measuring how many atoms changed state as a result. When the microwave frequency matched the atom's natural transition frequency exactly, the transition rate peaked. You could tune the microwave source to find that peak, and once you'd found it, you had a reference frequency of extraordinary stability. The transition frequency they were measuring, the one between two specific energy configurations of the cesium-133 atom's outermost electron. A pair of states, called the hyperfine levels of the ground state, was about 9,192,631,770 cycles per second. Nearly 9.25 billion cycles per second. A frequency so high it is in the microwave range, the same part of the spectrum as a kitchen microwave, though cesium clocks and kitchen appliances are not otherwise similar. Essen and Parry's clock was, in terms of accuracy, a revolution comparable to Huygens' pendulum. The pendulum had taken accuracy from minutes per day to seconds per day in a single step. The cesium clock took accuracy from small fractions of a second per day to something that, in principle, would not gain or lose a second in thousands of years. And unlike the pendulum, it was not sensitive to temperature in any significant way. It did not care about air pressure or gravity. It did not need to be level. It did not have a rod that expanded and contracted with the weather. It was locked to a quantum fact about a particular kind of atom. And that quantum fact was the same everywhere in the universe. In 1967, the 13th General Conference on Weights and Measures, the CGPM, the body responsible for the International System of Units, made it official. The second was redefined, not as a fraction of a day, not as a fraction of a year, but as precisely the duration of 9,192,631,770 periods of the radiation, corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. That sentence is a mouthful, and you don't need to hold it in your head tonight. What it means simply is this: a second is now 9,192,631. 770 ticks of an atomic clock. The Earth no longer defines the second. We fired it. The specific number, 9,192,631,770, was not arbitrary. It was chosen very deliberately to match the existing ephemeris second as closely as possible, which was itself chosen to match the historical mean solar second. The new definition was designed to be continuous with the old one, so that clocks didn't jump or skip, so that the astronomical records of centuries could still be read coherently. The number is a fingerprint of the cesium atom's quantum nature, but it is also, in a quiet way, an echo of all those centuries of watching the sun. Since 1967, the second has been an atom's heartbeat, and the clocks that count those heartbeats have kept getting better. Modern cesium fountain clocks, instruments like NIST F1 and NIST F2 at the National Institute of Standards and Technology in Colorado, and the NPL CSF2 at the National Physical Laboratory in Britain, work by launching clouds of cesium atoms upward through a microwave cavity in a low fountain shape. The atoms, cooled almost to absolute zero by laser beams, so they're moving barely at all, arc up through the cavity, come back down through it, and are detected below. Because the atoms spend more time in the microwave field, floating up and back down takes longer than a simple linear pass, they can be interrogated more precisely, giving a sharper, more accurate reading of the resonance frequency. These fountain clocks would neither gain nor lose a second in something like 100 million to 300 million years. Sit with that for a moment. 300 million years ago, the first reptiles were just beginning to appear on land, and the continents looked almost nothing like they do now. A clock that accurate would have been running continuously since then, and still not lost a single second. But that, extraordinarily, is not the end of the road. There are clocks now being developed and refined in laboratories at NIST in Colorado, at the PTB in Germany, at national metrology institutes around the world that use optical transitions in atoms, not microwave transitions like cesium, but transitions in the visible light range, which oscillate far faster, giving a finer-grained tick. These are optical lattice clocks, trapping atoms of strontium or ytterbium or aluminum ions in a cage of laser light, and measuring transitions that tick at hundreds of trillions of cycles per second. These clocks are so accurate that they would neither gain nor lose a second in tens of billions of years. The current age of the universe is about 13.5 to 14 billion years. These clocks are more stable than the universe is old. They are the most accurate timekeepers in the history of the world, and they are also leading candidates for the next redefinition of the second. A redefinition expected sometime in the coming years that will tie the second to an optical transition rather than a microwave one, buying still more precision. And here, drifting in the dark, is perhaps the strangest payoff of all of this precision. Optical clocks are so accurate that they can measure gravitational time dilation. That is Einstein's general relativity, the prediction that time runs more slowly in stronger gravitational fields and faster in weaker ones. At the surface of the Earth, we are in a gravitational field, and our clocks run slightly more slowly than they would out in open space. And the effect is not constant across the surface, it varies with altitude. Higher up, gravity is very slightly weaker, and time runs very slightly faster. How much faster? Enough that NIST researchers have demonstrated the difference between two optical clocks separated by a height of about 30 centimeters, about the height of a large hardback book. Raise a clock that much, and it measurably, detectably runs faster. Time runs at different rates at your head and your feet. Not in any way you would ever notice. The difference is incomprehensibly small, but real and measurable with the clocks we have now. You are taller than the time at your feet. This is not poetry, it is measurement. And all of this brings us, finally, to why any of it matters beyond the laboratory. The most immediate answer is GPS. Your phone, when it tells you where you are, is doing something that looks like geometry but is fundamentally a timing problem. Each of the roughly 30 satellites in the GPS constellation carries atomic clocks, cesium or rubidium, and each satellite broadcasts the current time as it knows it. Your phone receives signals from several satellites simultaneously. Each signal takes a slightly different amount of time to reach you, depending on how far away the satellite is. From those tiny differences in arrival time, your phone's processor triangulates your position. The key word is tiny. A timing error of 1 microsecond, 1/1,000,000th of a second, translates to a position error of about 300 meters. To give you location accurate to a few meters, the clocks need to be good to billionths of a second, nanoseconds. Atomic clocks make this possible. But there is a complication, and the complication is Einstein. The GPS satellites orbit at an altitude of about 20,000 kilometers. Up there, gravity is weaker than it is at the surface, so their clocks run faster than ours, by about 45 microseconds per day. But they're also moving at about 14,000 kilometers per hour. And moving clocks run slightly slow due to special relativistic time dilation, by about 7 microseconds per day. The net effect, satellite clocks run fast by about 38 microseconds per day relative to clocks on the ground. 38 microseconds per day. That sounds small, but at the speed of light, 38 microseconds corresponds to about 11 kilometers of position error per day. Left uncorrected, GPS would be useless in hours. Your phone map would be wrong by 10 kilometers by tomorrow morning. Einstein's relativity is not a theoretical curiosity applied to GPS. It is a daily engineering correction without which the entire system fails. The GPS engineers knew this when they were designing the system and built the correction in from the beginning. The satellite clocks are actually set to run slightly slow before launch, so that once they're in orbit and the relativistic effect speeds them up, they come out running at the right rate relative to the ground. General relativity, special relativity, atomic clocks, and the orbital mechanics of 20-odd satellites, all woven together invisibly, so that a small glass rectangle in your pocket can tell you where you are to within a few meters. This is what the Cesium second quietly runs. Not just GPS, financial markets depend on atomic time for timestamping trades and ensuring the order of transactions is legally unambiguous. Power grids use synchronized atomic time to coordinate the phase of alternating current across thousands of kilometers of interconnected network. Mobile networks, the Internet's timestamping protocols, data center synchronization. All of it running on atomic time distributed from national laboratories, an invisible infrastructure as fundamental as water or electricity, and almost never thought about. And yet, there is one last twist in the story. A small wrinkle that has been growing for years, and that forces us to confront, one final time, the gap between atomic time and the turning Earth. When the second was redefined in 1967, atomic clocks and the Earth's rotation were still in rough agreement. The new definition was calibrated to match the old one. But because the Earth's rotation is irregular and slowly lengthening, the two have gradually drifted apart. Atomic clocks run at a perfectly steady rate. The Earth does not. And over decades, that difference accumulates. The solution, from 1972 onward, has been the leap second. Coordinated Universal Time, UTC, the global standard that your phone and your computer run on, is based on atomic time, but it is kept within 0.9 seconds of UT1, which is universal time based on the actual rotation of the Earth. When the two drift far enough apart, the International Earth Rotation and Reference System Service, the EARS. The body that monitors the Earth's rotation announces that a leap second will be inserted. At the end of a chosen minute, instead of ticking from 23:59:59, the clock ticks 23:59:59, then 23:59:60, then 0:00. 1 extra second slipped in to bring atomic time back into alignment with the wobbling Earth. 27 leap seconds have been added since 1972. Always added, never subtracted, because the Earth has consistently been running slow relative to atomic time, just as we'd expect from the tidal breaking we talked about. But leap seconds cause problems. The internet was not designed to handle a minute that has 61 seconds. When a leap second was inserted in June 2012, it caused crashes and disruptions across hundreds of websites and services, Reddit, Yelp, LinkedIn, Qantas Airlines, all affected by a single extra second that their systems could not gracefully handle. The fix for most servers was to spread the adjustment out invisibly over a period of hours, a technique called leap smearing, rather than have the clock actually read 60. But the underlying problem remains. Atomic time and Earth time are different scales, and stitching them together periodically is genuinely difficult engineering. In 2022, the General Conference on Weights and Measures, the same body that defined the cesium second in 1967, voted to abandon the leap second by 2035 at the latest. The plan is to let UTC and UT1 drift apart, freely, without patching. The world's clocks will stop being tethered to the Earth's rotation entirely. This is, in a very literal sense, the final step in the long divorce of time from the planet, not just redefining the second, but letting the official count of seconds float away from the sunrise forever. How far they'll be allowed to drift before some other mechanism takes over, perhaps a leap minute once a century rather than a leap second every year or two, has not been fully decided. But the direction is clear. Atomic time wins. The Earth is officially no longer in charge. And then there is the final twist, the one that feels almost like the universe making a joke. Since around 2020, the Earth has, on some days, been spinning slightly faster than the long-term average. Not by much, by fractions of a millisecond, but fast enough that for the first time in the history of the leap second, there has been talk of a negative leap second, not adding a second, but removing one, letting a minute tick from 23:59,058 directly to 0000,000, skipping 23:59,059 entirely. A second subtracted from the calendar. This has never been done. Nobody knows exactly what it would break. The engineers who worry about these things worry considerably. A subtracted second is a harder problem than an added one, because systems that handle the possibility of 60 don't necessarily handle the possibility of a missing 59. And so, in an irony that seems almost too neat to be accidental, the Earth, the clock we spent all of human history trying to replace, is now, briefly, occasionally, outrunning our atomic replacements. The old clock, the one we fired, is running fast on some days, and the engineers are nervous. The planet, it seems, has not entirely given up. And now, in the quiet, here is where I'd like to leave you tonight. You've come a very long way since that Egyptian shadow clock. The L-shaped bar turned east in the morning and west in the afternoon, passing the sun's light into rough segments of day. You've been through the dripping water clocks and the mechanical escapements, the great pendulum swinging in Huygens' workshop in 1656, the lonely sea clocks pitching in the Atlantic on Harrison's long gamble. You've heard the Shortt clock humming in its near vacuum tank, steady enough to catch the Earth wobbling. You've traced the crystal and the quartz, the leap to the atom, the definition of a second cut loose from the planet entirely and welded to a quantum fact about cesium. And now you know what you're sleeping under tonight. Right now, wherever you are, atomic clocks are ticking in national laboratories and in the satellites overhead. They're ticking at frequencies calibrated to the vibration of cesium-133 atoms, corrected for Einstein. Synchronized across continents by systems that your devices connect to without your noticing. The timestamp on the last message you sent before closing your eyes was routed through a chain of technology most people never think about, in the heartbeat of an atom chosen for this purpose in 1955 and ratified in 1967. And the second that just passed, the one that passed just now, as you settle a little further into wherever you are, was exactly 9,192,631,770 vibrations of that atom. Not approximately, not close enough. Exactly, give or take the best measurement physics can currently make, which is accurate to within about 1 part in 10 to the 18th power. A number so precise, it doesn't have a comfortable everyday name. Time, it turns out, is not the gentle thing it seemed when it was shadows crossing sand. It is woven into the shape of space, it bends near heavy objects, it runs at different rates at different altitudes, it is counted by atoms and corrected by equations from a patent clerk in Bern. It is simultaneously the most familiar thing in the world. You've been living in it your whole life. You know exactly what it feels like, and one of the strangest things physics has discovered, a dimension of reality whose true nature is still not entirely understood. And all of this complexity, all of this precision, all of these centuries of ingenuity, from the Karnak water clock to the cesium fountain, were really in the service of one very human thing. We wanted to know where we were, when to plant, when to pray, when to sail, when to arrive. We wanted to agree with each other about what time it was, so that we could meet and trade and navigate and understand. The instruments got more and more refined, and eventually they got so refined that they revealed something unexpected. That the universe itself has a timekeeping preference, that atoms tick with a regularity the Earth cannot match, that Einstein's equations are not abstractions but corrections that must be applied to every satellite that helps you find your way. Somewhere in all of that, in the gnomon's shadow and the cesium's hum, is the whole of human ingenuity laid out in a single line. The desire to understand, the tools we built to satisfy that desire, the surprises those tools revealed when we looked more closely than we'd planned to. You are, right now, in the middle of that history. Not at the end of it. Optical clocks will redefine the second again, perhaps soon. Future generations will measure time with a precision that makes our current cesium clocks look like a sundial on a cloudy day. The story doesn't stop here, it just settles. For tonight. And I think that's a good thing to carry into sleep. That we are still, after all of it, in the middle of learning, that the second is still being refined, that the atom is still ticking, steady and indifferent and exact, while you drift. Wherever you're listening from tonight, whatever hour it is in your corner of the world, I hope you found something to carry. A small piece of the long thread. The shadow and the atom and everything in between. If you enjoyed spending this night together, drifting through all of this slowly, a gentle like or subscribe means a great deal to a sleepy little channel like this one. Small creators really do rely on your support to keep going. And I'd love to know where you're listening from and what time it is in your part of the night. Leave that for me in the comments when you wake. Until next time, rest easy. Good night, kiddo. Grandpa'll leave the porch light on.